Hello again, welcome back. This is the second part of the video lecture 7.3. The topic, in terms of the reading from your book, is Chapter 7, Section 4, Work Done by a Spring Force. And in the first video lecture, 7.3, I talked in great detail about the spring force and its behavior and the mathematical equation that describes it, which can be written in that form or that form, there and there, depending upon where the equilibrium is on the x-axis. And this famous formula is called Hooke's law. The main thing to remember is that Hooke's law is proportional to the amount the spring has been stretched or compressed. And the more you stretch it or compress it, the harder it is to stretch or compress it more. Okay? It's not a constant force. It's a variable force that's acting on a particle. All right, so I talked in great detail, and I did an example problem of applying Hooke's law to describe the spring force. That was right here, so I won't do that again. Now I want to talk about a very important next topic that goes with the spring force, and that is how much work does a spring force do when it acts on a particle? Now, just to be perfectly clear, let's imagine a scenario. I'm going to give myself a little bit of space up here and draw for you what I call basically the standard spring force situation. We've got a vertical wall for hooking up one end of the spring to. We've got a horizontal frictionless surface that we'll call an x-axis. And we've got a spring. One end is tied to this wall, and then the other end is tied to some kind of a block, which we just call a particle, like that. And the spring has what's called a spring constant, little k, in Newton per meter, which tells you how stiff the spring is, how hard it is to stretch or compress it. And we will assume that if the block is at rest, i.e. it's in equilibrium, with an acceleration equal to 0, and it's just sitting there at rest, we will put that equilibrium location on the x-axis at the origin, x equals 0. And when we do that, then the formula for the spring force acting on the block is negative kx, where x is the amount of displacement from equilibrium. So now let me draw a new picture. Let me draw, put in that x-axis again, let me draw the particle, the block, displaced from equilibrium. Maybe somebody has pulled it out to there, thereby stretching this spring. So now the windings, the coils, are farther apart by an amount x. Then the spring force will be opposite to that displacement. So in this case, the spring force would be in the negative x direction, and its magnitude is given by, well, the expression for it, including its direction, in fact, is given by Hooke's law. All right, so now what I want us to imagine is that this is a situation where this block is moving. And I don't care right now how it got started moving. Maybe I reached in and gave it a shove. Or maybe I reached in and pulled the spring away from equilibrium and then just let go. You can probably imagine what will happen after that's done. The whole block-spring combination is just going to what's said, we're going to call it oscillate. It's going to oscillate horizontally on this frictionless x-axis. And I want to imagine that the particle, the block, is moving between 2 points. We'll call them x1 and x2. And just for the sake of specificity, maybe this picture right here is the x1. And when I drew this picture, the block is still moving in the plus x direction, so that a little bit later, give myself a little more room here. The whole block spring combo is farther out here on the x-axis at a coordinate I'm going to call x2. Okay? So now the spring goes from the left side to there. Okay? So as this block has moved from x1 to x2, there's been a spring force acting on it. And if I have a force and a displacement with a component of the force and the displacement in the same direction, or along the same axis, then there's work done by that force. I want to be able to calculate the work done by a spring force in a situation like this, when a particle goes from x1 to x2. Okay? That's my motivation and my trying to give you a physical scenario that you can picture in your head what we're talking about. All right. So how are we going to do this? How are we going to calculate the work done by the spring force as the block goes from x1 to x2? All right. Well, here's the first thing that I've said already, but it bears repeating, and I'm going to emphasize it. The spring force is not constant. As that block moves from x1 to x2, the spring is getting stretched more and more. The spring force is getting bigger and bigger and bigger in magnitude and pointing to the left. So as the block moves from x1 to x2, the spring force on it is changing. In magnitude, it's not constant. So we cannot use this formula over here to calculate the work done by the spring force. F sub s, spring force, dot delta r, displacement. Can't do it. Wrong. Well, we can do it, but the answer will be wrong. Right? Because that formula, understand why? That formula for the work that I'm saying to you is wrong. It was a definition of work, but it was the work done by a constant force. After all, it assumes one vector, F sub s. But if the force is changing, what's the one vector you pick? Right? That whole formula up there, I just keep saying it over and over, because I want to emphasize how important it is to understand. You can't use that formula directly. So now we seem to have a real quandary. How do we find the work done by the spring force? Because I still want to know how to do it. Here it comes. Here's how we're going to do it. Here's the approach. I'll call it a trick. But what I'll really describe it as is ingenious. It's ingeniousness. The trick comes from mainly two people, I suppose. Hopefully I'm not doing an injustice to history here. But the people are Newton and Leibniz. Think of his name for a minute. Newton and Leibniz. And they hated each other, or at least they were rivals and all that stuff. But that's all part of history. But here's the brilliance of what they are thinking, what they're doing here. Because it's the brilliance of calculus, again. Here's what we imagine doing. Let's imagine dividing up the x-axis into small segments. Each has a size delta x. Okay? So imagine breaking up, I'll go back up here, to the x-axis between x1 and x2 into a whole bunch of little distances like that one of length delta x. And there's a whole bunch of them, starting at x1 and ending at x2. Okay? I've also drawn that below in a plot of force versus x. F sub s on the vertical axis, x on the horizontal. Over here is x equals 0. So I'm not showing you to the left of equilibrium here, only to the right, just so the picture isn't too complicated. I have plotted the spring force, negative kx. When the horizontal axis is x, negative kx is a straight line with no intercept and negative slope. Slope is negative k. So that's this line right here. That goes to the origin and has a negative slope going onward and downward forever. And I've also marked the points x1 on the x-axis and x2. And I've imagined dividing up the region between x1 and x2 into a whole bunch of little lengths delta x. I've emphasized one of them, but all those lengths delta x, there's a whole bunch of them in there between x1 and x2. All right, now here's the trick, or the next part of the trick. We will assume over each length delta x that the spring force is approximately constant. And so we will assume it's constant. So I show that for this one rectangle, delta x, by showing this downward arrow saying that's the average spring force value over that interval delta x. And the j there is just saying this is the jth rectangle. Of course, you can count them in the picture I've drawn here. First one is right here. There's the first rectangle. Second, third, fourth, fifth, sixth, seventh, eighth. I've drawn 8 rectangles between x1 and x2. So the one that I have labeled delta x, although they all have width delta x, but the one I've singled out to focus on is the fourth one. but we'll just use this generic subscript j to say it's the jth rectangle, where j in this case can be anything between 1 and 8. I happen to draw the picture there for the average spring force where j was equal to 4. And what we're saying is over that interval delta x, you take the average value of the spring force in that interval, right there at the end of the red arrow, right there, and I assume that the force is constant. So I draw a horizontal line right there at value F4 average, which would be negative k times the x value at the center of that rectangle. And then, just from the component form of work, F sub x times delta x, the work done by the spring force over that displacement delta x is written right here. The force, the x force, times the x displacement. The x spring force over that interval times the size of that interval. But that just ends up being, if I look at that fourth little blue rectangle there, the width of the rectangle, delta x, times its height, fj average. So that's just the area. The work then is the area of that rectangle, width times height. Now that's just the work done over that one particular interval delta x, but I've got 8 of those intervals. So I have 8 rectangles, each with a different height. So what I have to do is shown over here, at least in principle. I have to add, this notation means sum, S-U-M, add, sum over all of those rectangles, j, the work for each rectangle, delta W sub j. Or sum over all those rectangles, j, the force for each rectangle, Fj average, times the width of each rectangle, delta x. Okay? Okay, so the trick is to divide up the region between x1 and x2 into little intervals, and just assume that over each interval, the spring force is constant, and so we can use the way to calculate work that we did before for a constant force. But you got to do that for each of those little rectangles and then add them all up, all the works, and then you get the total. But wait, I hear you say, but wait a minute, that's not a very good approximation. What you've really got is that straight line plot of the spring force, and you're kind of breaking it up into these jagged flat parts, and you're finding the areas of these rectangles that go with each of these flat parts, and you're adding those up, but it's not really true that over one of your intervals delta x, the spring force is constant. Because delta x is some amount of distance along x, and the spring force depends on x. So it's not really true that the spring force is constant over each one of my delta x's. So this expression right here, for the work from each one of those rectangles, which is based on the assumption that the spring force is constant over that rectangle, isn't really true. That's why I put the approximation symbol right there in the work formula. It's only approximately true. Well, that's not really good enough. Can't we do better? How about if we do a better approximation? What if I imagine that instead of dividing the region between x1 and x2 into 8 rectangles of equal width delta x, I draw 10 rectangles, still between x1 and x2. Now they'll each have a delta x, but it'll be smaller than the delta x here, right? Because there are 10 rectangles now, not 8. And so the width of each rectangle now is narrower, so the delta x is narrower. And it's still true that the spring force is not constant over a given delta x, but the delta x is now shorter, so it's not as bad of an approximation. But it's still not exactly right. So instead of 10 rectangles, let's imagine 20 rectangles between x1 and x2. Now the delta x for each one of the rectangles, because there's 20 of them now, is very small. And to assume the spring force is constant over the delta x or one of those very small rectangles, that's not so bad an approximation. Well, if that is how we're going to do it, then let's just conceptually say, fine. Let's imagine going into a limit where the number of rectangles gets bigger between x1 and x2, and the width of each rectangle gets smaller and smaller and smaller. So what we're going to do is imagine passing to the limit as delta x becomes vanishingly small. And that means, in using calculus notation, we're going to take what's called the limit as delta x approaches 0. Now, we don't really mean 0. This is where your calculus professor is probably going to do all kinds of fancy explanations for you. Because when we say delta x becomes vanishingly small, and we do write it, limit as delta x goes to 0, we really mean that delta x becomes infinitesimally small displacement along the x-axis, which we write in calculus as dx. It's infinitesimally small. And over that infinitesimal dx, it's okay to say the spring force is constant. And it's not an approximation. It's exactly true, because that's an infinitesimally small displacement. But then you still got to take all the works for all the little rectangles, which amounts to taking the area of all the little rectangles and adding them all up. But now they're an infinite number of infinitesimal rectangles. And that process of taking that limit of the sum like that produces what's called, in calculus, an integral. And that's what this expression is right here. We now have what's called an integral for calculating the work done by the spring force. And the symbol for an integral, we'll draw it over here to the side, is to draw a long stretched out S, a rather elaborate S symbol. S for sum, S-U-M. And you take the spring force at whatever x you're at, that means it's a function of x, times the width of the little rectangle where that x is, dx. And then the next convention is to put what are called limits on this definite integral. The lower limit is the x value where the blocks or the particle started, x1. And the upper limit is the x value where the particle stopped. Well, not stopped, but where we called the stop point, x2. But it still boils down to taking the area of an infinite number of infinitesimal rectangles and adding them all up. At least geometrically, you can think of it that way. So, geometrically, an integral is equivalent to the area under a curve. Very handy thing to remember in physics. Integral is an area under the curve. If I'm integrating the spring force, as I am to get the spring work, Ws is equal to the area between the plot of f sub s and the x-axis. So I'm going to show you that in a graph. But before I do that, I want to show you an animation from Wiley Plus. That is our standard scenario of a horizontal frictionless surface with a block and a spring with a spring constant K, and one end of the spring is tied to a wall, and the other spring is tied to the block. The block's at rest right now at equilibrium, which we take to be the origin. So this picture is going to take x1 to be 0. And when I run the animation, it's going to move to the left because I'm going to imagine that I gave it a shove. And it's going to travel from x1 to x2, where it will momentarily stop. x2 happens to be at 1 meter in this case. And then it would come back, but we're not going to look at that. And what I've done in this animation is I've divided up the region between x1 and x2 into just 2 rectangles. 2 big, wide rectangles, each 0.5 meters wide. And within each rectangle, I'm assuming the spring force, at least I can use in the spring force that's an approximate that's equal to its value at the middle of that rectangle. And then I'm going to show you the animation. It's going to show you the exact spring force that's just smoothly getting bigger as the spring stretches more. And then the approximate spring force, which is constant over any given rectangle. And then when you transition from one rectangle 1 to rectangle 2, the spring force jumps to the new rectangle spring force. So let me just run the animation a couple of times so you can see what I'm talking about. Okay, so when I got the block in the region that I would call rectangle 2, the spring force, the approximate spring force, the dashed arrow, is constant, equal to the value right there at the middle. Okay, and well, I should be clear. Apparently, this approximate force is at the beginning of the interval. So, sorry, that's not quite what it was supposed to look like. Somebody didn't catch that. It's looked like it's using, for the approximate force, the value of the force at the beginning of the interval. It's okay. All I want you to see here is that there's an exact force that's smoothly getting bigger as the spring stretches more, and an approximate force that's constant over any given one of those rectangles. Point being, the approximate force, the dashed arrow, not a very good representation of the exact force. So that if you find the area under these two rectangles that you see, the smaller one and the big one, and add them up and call that the work done by the spring force, it's not a very good approximation to the actual work. So let's break up this interval of 1 meter into, well, let's say 4 rectangles. Now each one is 0.25 meters in width. Now let's see how good the approximate force is relative to the exact one. Well, the dashed one is, it's still choppy, but it's a little better version or representation of the exact force. But still, the work I get by adding up the areas of the 4 rectangles is not going to be that good of an answer for the work. So let's put in more. Let's go to, how about 8? Like I showed you on my drawing. Now see how good the approximate force is. It's a better approximation to the exact force. And the area under the 8 rectangles added up is a better approximation to the exact work. Go to 10 rectangles, each now smaller than before. And the approximate force is a better representation of the exact force. And the area of under the 10 rectangles added up is a better approximation to the exact work. This animation will let me go up to n equals 40. You can hardly even visualize the 40 rectangles because they're so narrow now. But let's see how good the approximate force is. Look at that. It's following the exact force very closely. And the area under those 40 rectangles added up is a very good approximation to the exact work. Okay? All right, so that's just the idea behind it. But the point is that this integral of the spring force over the x-axis from x1 to x2 is geometrically equivalent to the area. We say it's the area under the curve. So let me show you in the next picture exactly what I'm talking about. Right here. It's the same plot of the spring force, right? Versus x. And I've picked starting point x1 and an ending point x2. And now what I've done is I've shaded the area between the actual plot of the force. Try to be clear. That's that straight line going down, because that's Hooke's law. I want the area between that curve, the x-axis, and x1 and x2. It's that shaded area right there. That area is equal to the integral of f sub s dx, and it will be the answer for the work done by the spring force. So all I have to do is find that shaded area using geometry. Note that it's convenient to divide this area up into 2 parts, part 1 and part 2. Part 1 is a short rectangle, and part 2 is a triangle. And I just need the area of each one of those, symbolically. So that's what's going to happen next. Let's do the rectangle first. I need this area right there. Well, the area of a rectangle is length times width, or length times height, whatever word you want to use. The dimension this way multiplied by the dimension this way. Okay, all right. So that area is what we're going to start with. There's the width, x2 minus x1, right? That's how long the rectangle is from there to there. All right, so I multiply that by the height of the rectangle. Now here it's a little bit subtle because the plot is below the x-axis. So you have to treat that as negative height. You're going down instead of up, right? But the height down is negative kx1. So it's that product of width times height. is the area of that rectangle. Now I'm going to add to that the area of the triangle, area 2. Right? And the area of a triangle is 1/2 width times height. So here we go. 1/2. The width is still x2 minus x1, right? Same width as the rectangle. But the height is between that point and that point, and it's going down, so it's going to end up being negative overall. It's negative kx2 minus negative kx1, which is negative kx2 plus x1. Now the next thing you do, I'm going to let you do this on your own because it's just algebra, is you multiply all this out, right? You got this negative kx1 to distribute through the x1 minus x2, and then that's what you have here and here. And then you've got a product of two binomials that you've got to multiply out and then multiply out by a 1/2. And then you've got to simplify and gather all the terms and make it as simple as you can, and you get the result in this boxed formula. This is the formula for calculating the work done by a spring force for a particle moving along an x-axis with equilibrium at x equals 0. What you get is 1/2 times the spring constant times the initial x value squared, x1 squared, minus 1/2 times the spring constant times the final x value squared. If you want to factor out the 1/2 k, it's 1/2 k times, parentheses, x1 squared minus x2 squared. Let me emphasize, all this pictures I was telling you here was to try to give you some understanding for how we're going about calculating the work done by this variable force called the spring force. But at the end of the day, the main thing you have to be able to do is use the equation in the box correctly. You don't have to repeat this derivation every time you need to calculate W spring. If you have a problem with a particle moving along an x-axis with equilibrium at x equals 0, and you need to calculate the work done by the spring force between a point x1 and x2, just use this formula. But x1 is the initial value of x, and x2 is the final value. Now, work is a scalar, so it doesn't have a direction, but it can sometimes be positive and sometimes be negative, depending upon what's happening in the situation. So here's another useful thing to ask ourselves. Under what conditions is the work done by the spring force positive? And conversely, under what conditions is the work done by the spring force negative? Let's talk about that for just a minute. Let me do the positive work case. Under what conditions is the work done by a spring force greater than 0? Again, I'm imagining that block on the x-axis. It's going from x1 to x2. All I have to do is look at this formula up here. I think the easiest version to look at is that last version right there. How can I get that to be positive? When will it be positive? Well, the k is positive. So the way I know I'm going to have a positive value for work is if x1 squared is larger than x2 squared. Yes? Then the things in the parentheses, I'm taking the bigger number minus the smaller number, that's going to be positive. Now remember, x1 is the initial x, and x2 is the final x. So if x1 squared is larger than x2 squared, what does that mean physically has happened? It means the particle moves closer to equilibrium, because equilibrium is at 0. And x2 squared is smaller than x1 squared, so it has to end up closer to 0 than it started. So spring force does positive work when the particle ends up closer to equilibrium than where it started. For example, let me draw a little sketch. There's our wall. There's our frictionless x-axis. There's equilibrium, abbreviated like that, equil, period. Let's say the particle started out there, x1. That's where the block started. Let me draw over here just so that we have kind of a symmetric view, negative x1. Okay? So it starts at x1, and if the work done is going to be positive, then x2's got to be closer to equilibrium than x1. So all I'm saying is that x2 can be anywhere in the region that I'm kind of shading here along the x-axis. I'm shading it purple, between x1 and negative x1. So x2 can be anywhere in this shaded region, and we'll have positive work done by the spring. Okay? Because the particle ended up closer to equilibrium than where it started. Now conversely, when can you get a negative number for the work done by the spring force? Look back up here to the expression I have circled in red. The way to get that expression to be negative, it is possible, is to have the x1 squared be smaller than the x2 squared. Oops, pardon me. Line there I don't want. So I get negative value for the work done by a spring force when x1 squared is smaller than x2 squared. Remember, equilibrium is at the origin. x1 is initial, x2 is final. So if x final squared is larger than x initial squared, physically that means that the particle moves farther from equilibrium compared to where it started. Farther from. What would that look like, potentially, on our standard picture? Well, let's say that the particle started out, say, maybe here, but let me draw the symmetric version of it on the left, negative x1. Now it's got to end up farther from equilibrium than where it started. So it's got to be either extending on out this way, to the right of x1, that would be an x2 squared larger than x1 squared, or this way, at least as far as it can go, extending that way, because that would give you an x2 squared larger than an x1 squared. So now what I'm saying is that if you're going to have negative work done by the spring force, that the particle is going to be somewhere in the purple shaded region there. Point being that it has ended up farther from equilibrium than it started. All right, so let me emphasize, a lot of this was just giving you the ideas building up to how we calculate work done by spring force, and I do want you to have some basic understanding of those ideas and how we use them. But at the end of the day, you must understand how to interpret and use the equation in the box. That's the formula for calculating the work done by the spring force. That's what we will go to whenever we need to calculate work done by spring force for a particle moving on an x-axis. And we'll be practicing with that in class. But for now, that's all for this video.